We now want to consider our case where we're very far away from our source distribution. And what that means is if we look carefully at these terms, s plus and s minus, notice that they go like a times a distance y, but this is at best 1 over r. And over here it's a squared over r squared, so that goes like 1 over r squared. So in both of these cases, the quantity s plus and s minus, they are both very small. And that's what we're going to exploit in this expansion, because we have the result of applying the binomial theorem that this quantity is 1 minus 3/2 s plus. Now, the next term in here turns out to be 15 over 8 s plus squared, and that series goes on. But this is the term that we're going to ignore. And by ignoring that term, we can write out our expansion in the following way. We have that 1 over 1 plus s plus to the 3/2 is approximately 1 minus 3/2 s plus. And similarly, 1 over 1 plus s minus to the 3/2 is approximately 1 minus 3/2 s minus. And now we can treat each of these terms separately in the expansion. And let's just work first with the x component. We have that factor kq over r cubed on the outside times a factor x. And now we're using both of these expansions. And so we have 1 minus 3/2 s plus minus 1 minus 3/2 s minus. And so you can see that the 1's cancel. We have the factor 3/2 on the outside. And we can write that as minus 3/2 kq x r cubed times s plus, that's where the minus is, minus s minus. Now, when we look at s plus minus s minus, which we have over here, we can see that the a squared over r squared terms are canceling. And we just have these first terms, minus 2y over a r squared minus 2ya over r squared. So this becomes minus 3/2 kqx over r cubed. When we subtract these two terms, s plus minus s minus, we get a negative sign, 4. So we have a minus 4 ya over another factor r squared. We're now approximating this. And so we get that ex xy. The two minus signs cancel. 6 kq xy a over r to the 5th. And in this particular problem, our magnitude of our dipole moment is 2aq, because it's a distance 2aq apart. So we could write that as 3kp xy over r to the 5th. Now, you might look at this and think the field is falling off like 1 over r to the 5. But that's not quite right, because x and y are at the location of the field points. They're on the same order as r to the 5th. So this is really showing us something that falls off like 1 over r cubed, which is not a surprise, because the whole distribution was neutral. So it shouldn't have a 1 over r squared term associated with point charges. But the leading order term is approximately goes like 1 over r cubed. Now, the other term, it's a little more complicated. So let's see what we can get. We have, again, kq over r cubed. We have, this is a little messier, 1 minus a times 1 minus 3/2 s plus. That's expanding the s plus term using our expansion. A minus sign, 1 plus a times 1 minus 3/2 s minus. Now, this one's a little bit trickier. Let's just look at some of the things that appear in here. We really have to expand these terms. And what we'll see is the y's are going to cancel. Maybe it's just a little bit wiser to expand all these terms out. We get y minus a. And over here, we have minus 3/2 y s plus. We have plus 3/2 a s plus minus y plus a. That's the first one. And the next one is y. There's a minus 3/2 s minus y. And finally, there is the term minus 3/2 a s minus. So this one was a little bit more complicated. And now what we want to do is just clean up that term. We'll need a little room over here to do that. So let's just get rid of those terms. We don't need them anymore. And now let's look carefully at what we have. The y's cancel. The minus a does not cancel. And we have an extra term in here. So what we get is that e y xy is kq over r cubed. We have a minus a and a minus a. So that's minus 2a. I'll just denote the terms that have canceled. Over here, we have minus 3/2 y s plus. And over here, we have minus 3/2 s minus y. So that looks like minus 3/2 times y times s plus minus s minus. And that takes care of those terms. And our last terms, we have 3/2 a s plus minus minus 3/2 a s minus. So we get a 3/2 a s plus plus s minus. Now, that was a little complicated. We've already seen that our s plus and s minus term, we have to now subtract these and add them. And so we get kq r cubed minus 2a. Now, when we subtracted those, there's a minus 2y over r squared minus minus 2y over r squared. That's a minus 4y over r squared. So we have minus 3/2 y times minus 4y a over r squared. And our last term is over here. That's plus 3/2 a. And when you add these together, these two terms cancel, and we get a factor of 2a squared over r squared. We're almost there. Now, what we want to look at is these terms. Notice we have a factor 2a, and over here we have a factor that goes like a cubed over r squared. So when we compare this one to that one, it is very small. We have to be careful with our, yeah, we're OK. So this term is much smaller than that term, which we can neglect. And so this term we're going to neglect because it's much smaller than the leading order term, and we have k cubed r cubed times minus 2a. Over here, we can write that as 6 y squared a squared over r squared. And now, again, let's just check orders. Why didn't we throw this term away, a squared over r squared? But remember, y is the position of the field point. It can be on the same order as r squared. So we should have no factor a squared here, and that's a nice check because these have the same order. This can't be right. And notice that I missed my factor. I added an extra a there. And so there's the result for the electric field, and there is the x component and the y component. These expressions are complicated, and next we'll look at how to think about those in a different coordinate system.